All right, well, thank you very much for the introduction and for the opportunity to come talk here. So the title of my talk, An Ecological Approach to Diet-Based Cancer Therapy. Oh, back. So there's actually a number of things that I want to talk to you about. So I want to talk about diet, ecology, about cancer, and then get into what we call eco-oncology. And this is something that we believe is actually going to be the new way that oncologists are going to practice oncology in the future. So a little bit about ecology and a little bit about the journey of how I got there. So I'm a neural stem cell biologist. I'm not a cancer biologist. And when I went to the University of Florida, it was actually my first week I was there. My lab was empty. People hadn't come from Australia yet. I'm in my office writing on a grant that didn't get funded. This girl knocks on my door, introduces herself, and says that she saw an article in the newspaper that I'd moved here and that I studied brain cancer stem cells. And she had these nanoparticles that she wanted to use to target the brain cancer stem cells. And I looked at her and I went, "How old are you?" She goes, "Well, I'm 15. And I'm like, "What are you doing at the university at 15? And number two, where did you get your nanoparticles from?" And very matter of fact, she just says, "Oh, well, I make my own nanoparticles because I've been working at the Nano Institute for the past year." So both of her parents are professors at the university. I meet her father. We become buddies. And he is a card-carrying ecologist. And so we realized shortly that we actually have the same job. So I look at birth rates and death rates of tumor cells. I look at predators like chemotherapy and radiation. And he does the same. He goes out in the field and looks at wildlife populations, looks at birth rates, death rates, and predators as well. And then we realized we have another similarity, is that neither of us actually understand our population very well. The ecologists don't understand the entire ecosystem, and us as cancer biologists, we don't understand the way everything about how cancer cells work. But that's where the similarity ended, because the ecologists have done a fairly good job of managing wildlife populations and managing pest populations, whereas the cancer biologists have not done as good of a job. And so just to kind of make this point, here is an anthill, and so you can see on the left-hand side, it just looks like a big mess, a big pile of dirt. And you look at the middle panel, and you see there's a lot of structure to that anthill. And then you look at the panel just on the right-hand side, and all of that structure is created by these individual elements, individual agents, or these ants. And this is a brain tumor. This is a stage 4 glioblastoma. On the panel that's on the left-hand side, you can see sort of that white contrasting. That's the tumor there. When you section it and you stain it, you see there's a lot of organization. So it's not just a mass, but rather there is order to it. And when you look at what gives that order, it's all those individual cells. And so one of the similarities between the ecology world and between the cancer world is this thing of complex adaptive systems. So when you take an individual agent, like an ant or a tumor cell, you put a whole bunch of them together, like hundreds of millions to billions of them, you allow them to communicate, you give them some time, and they form these complex, adaptive, and very robust systems. So really, my talk is about when any oncologist meets an ecologist, and what does this ultimately lead to? Now, the second thing I want to talk a little bit about is diet, or give a little introduction to diet. And we've probably all seen this saying, "Let food be thy medicine, and medicine be thy food." And even though we're not here yet, when you look at the nutritional world, this is where they're heading. And so I think we all understand the value of nutrition for maintaining health. But what is starting to happen is there's getting to be a shift of the value of nutrition for actually fighting disease. So what about cancer? So you go to the NCI website and you look up diet and cancer. This is not diet treating cancer. This is the influence of diet and the occurrence of cancer. And here's what you find. Things like antioxidants, in humans, there's not been any data demonstrating that antioxidants play any role in cancer. You look at artificial sweeteners, and there's no clear evidence that artificial sweeteners have anything to do with cancer. Charred meats, again, there's some data in animals, but there's no human data to support charred meats have any evidence or any role in cancer initiation. You go to vegetables like broccoli, Brussels sprouts, for instance, same sort of thing, animal data, but there's no human data. And then you go to vitamin D, where there is epidemiological data, but there is no human clinical intervention data supporting that vitamin D has any role to play in the development or the progression of cancer. And now, what I really want to talk about, though, is diet and cancer treatment. So you go to a literature search, and nothing pops up. There's very little literature out there about it. And there was this one study It was in the Journal of the American Medical Association, and they looked at women who had breast cancer, and they were looking at reoccurrence of breast cancer and looking at basically, how many vegetables they were eating. They did a dietary survey, and what they found is among survivors of early-stage breast cancer, adoption of a diet high in vegetables, fruit, and fiber, low in fat, did not reduce the reoccurrence of cancer. So the whole issue of diet and cancer really is this question mark. It's sort of a black box. We really don't know, and there's not a lot of solid data on this. Now, what about cancer as an introduction? So basically all cancers could be defined as uncontrolled growth and spread of abnormal cells. But one cancer isn't the same as the next cancer. So cancer is actually a constellation of diseases that share that commonality of uncontrolled growth and metastases. And so the idea that when you're treating cancer, are you treating one disease? No. When you're treating cancer, breast cancer, you're probably treating one disease versus when you're treating brain cancer, a very different type of disease. And so this kind of partially explains some of the slides I'm about to show to you. So this is demonstrating that cancer is soon in developing nations to become the #1 killer. It already is in Australia, and probably within the next decade or two it will be in the United States. This is for two reasons. Number one, numbers of people dying from cancer is increasing, primarily due to our aging population. But number two, we've actually done not a bad job of dealing with heart disease. Now, things are getting better. If you look at 5-year survival statistics, they're trending in the right direction. The problem is that the gains have been relatively modest. And if you look at advanced cancers or the most common types of brain cancer, it's actually quite dismal of how the outcomes have changed over the past couple of decades. And this is some statistics. This is looking at deaths per 100,000 in the United States from 1950 to the year 2005. And what you can see is that the deaths by heart disease and things like stroke have gone down about 60 to 70%. So we've made a real difference. Medical research has made a real difference in those diseases. When you look at cancers overall, it's gone down by 5%. So in 1971, Richard Nixon signed the Cancer Act, sometimes called the War on Cancer. Since that time, the US government alone has spent upwards to about $90 billion on cancer research. Now, that's not talking all the other countries in the world, biotech companies and pharmaceutical companies. And what we have to show for that, again, overall, is we have a 5% increase. Another alarming statistic is looking at the cost of an average cancer treatment. And this is the year 2000 compared to the year 2012, and the costs have gone up dramatically. And what we have to show for it, again, overall, is not that large. And even though our 5-year statistics are actually getting better, there's a strong argument to be made of what do increased survival at 5 years actually mean. And there's been several articles that have come out to the same conclusion. And it states that changes in 5-year survival over time bear little relationship to changes in cancer mortality. It's that we have better diagnostics. And so to give you a little bit of a ridiculous example, there's this thought that may be a little bit urban legend that we all have cancer cells in us. So let's say I had a way of diagnosing one cancer cell and I screen everyone. Well, everyone would have cancer. Immediately, our 5-year survival statistics would absolutely skyrocket. So the question is the increase in 5-year survival because of better treatments, or do we have earlier diagnostics? So I'm not a cancer biologist. I really am a neural stem cell biologist. And so what this tells me when I start looking at all of this, now except for a few notable exceptions like some of these diseases or some of these cancers, and there are others in this category as well, is it tells me that the contribution of our standard of care, and particularly chemotherapy, to cancer outcomes is actually quite small. This is big business. Chemotherapy accounts as about a $23 billion a year industry in the United States alone. And what we've been doing is basically the same model. We've been looking at sort of the genetic causes of it. We've been targeting specific pathways, usually individual pathways, one at a time with kinase inhibitors or using a toxic drug. And we've been doing it again and again and again and again. And this reminds me of the definition of insanity. Doing the same thing over and over again and expecting that you're going to get a different result. How many failed kinase inhibitors do we need before we say stop? Let's try something a little bit different. So now this gets us into the eco-oncology. How can you marry these two things together? And really the question here, what if I, as an oncologist, think like an ecologist. Can we get better outcomes? And so to start to think like an ecologist, we can talk a little bit, there's this handbook called Integrative Pest Management. It was developed in the 1960s, really came out of decades of a lot of high usage of toxic pesticides like DDT, for instance. Today, if you have a pest population, you open up the handbook of integrative pest management and you use that as your guide to decide how am I going to deal with this pest. And some of the key elements of this are things like, is that you do not try to eliminate a pest population. You're unlikely to do it, you're usually going to fail, and when you try to eliminate it, number one, not only do you damage the environment, but the pest usually comes back worse or more resilient than when you started. So second, the goal is actually to maintain the pest at a level that is economically viable. So if my pest is eating 90% of my crop, that's not economically viable. But if the pest is eating maybe 10, 20% of my crop, I can deal with that and I can still, harvest a crop that makes sense economically to do that. And you do this by reducing the selection pressure, because in ecology, anytime you put a selection pressure on a population, you force it to evolve. The stronger the selection pressure, the quicker that population will evolve. And by doing this, you stop the pest from gaining resistance. So you'll always have that pest being able to be sensitive to that treatment that you have. Again, you're not going to eliminate it, but you're rather going to control it and you're going to manage it. And so some of the strategies for resistance management, so sort of three general strategies that are used. One is called management by moderation. And this is where you are trying to preserve the susceptibility genes in that organism, and you do it by reducing sort of the chemical pressure that you put on it, because you don't want to drive those genes that make them sensitive, you don't want to drive them out of the population. Second is management by saturation. And this doesn't mean that I'm going to just throw everything at it. What it means is as your population is beginning to search for different ways to escape that selection pressure, you're hitting it with something else. So it's kind of like, you're driving, there's a roadblock here, and you decide, well, okay, I'm going to go to the left. What you do is you put a roadblock over there. And when it decides it's going to go straight, you put a roadblock over there. So you're trying to adapt to how the population, the pest, is adapting. And last is management by multiple attacks. So this is where you use multiple agents, each agent sort of being below that threshold of inducing resistance. But if you just use one agent that's below that threshold, you don't get much of effect. But if I can use multiple agents, I get this cumulative effect. And so kind of with these thoughts in mind, we sat down in the lab, sat down with my ecology guru, and we had a brainstorming session. And what we wanted to do is we wanted to develop non-toxic treatments that could be stacked and used together with conventional treatments. In choosing these, we wanted therapies that were going to be safe, but demonstrating efficacy as well. And we also wanted to move to clinical testing as quickly as possible, because our preclinical models are informative. They tell us something, but they're not predictive. The only way you're going to know it works in a human is you simply have to go do it in a human. And we also saw something that was practical. And by practical, I also mean cost-effective, because we don't want to be the next $200,000 a year drug that comes out for a cancer treatment that increases life expectancy by a month, because that's killing the system. The system simply cannot sustain that. So part of my background is I have a doctorate degree in Chinese medicine. I used to be a herbalist and an acupuncturist. So it's got me thinking about some of the things that I did when I was practicing Chinese medicine, got me thinking about natural products. So look in the literature, there are about 60, 70 natural products that have anti-cancer effects, way too much to study. So we set sort of an inclusion criteria of what we wanted to do. We said things like there had to be a substantial body of evidence and efficacy in tissue culture and animal models. There had to be dozens to hundreds of papers on that natural product. There had to be evidence of safety at doses that we knew from the literature could be effective. We wanted things that had GRAS status, or generally recognized as safe status, because remember, one of our criteria, we got to get into the clinic quick and test it in people. We don't want to spend a decade playing around in animals and then go find some weird effect when we move to a human population. This was actually the hardest thing to overcome. We had to find a reputable supplier of the product, and that's actually really difficult, because the whole natural product, health food, nutraceutical world in the US and in a lot of countries is completely unregulated. And there also had to be known mechanisms, because we expected to fail, and if we knew some of the mechanisms, we could then make logical decisions on what to do next. So we did this, we narrowed it down to about half a dozen things. We did a screen of all the combinations, and we came up with 3 things that we call a polymolecular botanical drug. And this is a combination of these 3 agents. One is a catechine from green tea. The second one is curcumin, but a specific type of curcumin that has very high bioavailability. And the third, that we believe the active compound is called sulforaphane. And you find sulforaphane in things like broccoli, Brussels sprouts, cabbage, for instance, but the highest concentration is actually in broccoli sprouts. And so you know the alfalfa sprouts you get at the grocery store? Sometimes you'll see broccoli sprouts beside it. That has the highest concentration of sulforaphane. So we literally use freeze-dried broccoli sprouts that we get from a very reputable company out of California. So we combine those together, we give it a name because my colleagues like names like this, and we call it epidipherphane. Now, at the same time, because remember, well, we need to be able to target at multiple levels. And so this got us thinking about the metabolic aspects of cancer. So I'm just going to blow through this because all of this is going to be a repeat. But basically, at the end of the day, there was a student in my lab that developed what she calls the modified ketogenic diet. And in essence, what it is, it's basically about 10 to 20% carbs, medium chain triglyceride, and with about 30% protein in it. So there are at least 2 physiological things that happen on the ketogenic diet. Glucose goes down, ketones go up. And when we compare the modified ketogenic diet to the ketogenic diet, they looked identical in glucose. It looked identical with the rise in ketones. And so now we go in and we start studying this in our animal models. And so this is a survival curve, Kaplan-Meier survival curve. This is an animal that has a very aggressive high-grade glioma, a human a brain tumor. And we find that epidipherphane on its own enhances survival. When we looked at the classic ketogenic diet and Regina's modified ketogenic diet, it increases survival, and the 2 performed identically. And when we combine the epidipherphane and the modified ketogenic diet, and at the time we were calling this combination Cancerna, so you're going to see that pop up a few times. When we combine them together, we got a doubling of effect on survival. Now, we never intended that this would be a standalone therapy. We always intended this would be used together with standard of care. So the standard of care for high-grade gliomas is a drug called temozolomide, chemotherapy drug, or TMZ for short. And this is looking at tumor progression. And you can see the red is the control. And you see over time, the tumor is progressing. It's starting to grow. And the yellow and the purple in the middle is the chemotherapy drug or the Cancerna protocol. But when we combine the 2 together, we actually get an additive type effect on overall tumor reduction in tumor progression. People with high-grade gliomas, about 50%, so I'll tell you a little bit about this. It's called a glioblastoma. The mean time from diagnosis to death is about 12 months, and less than 5% of the patients survive for up to 5 years. About 50% of those patients are resistant upfront to temozolomide, and the other 50%, virtually all of them will become resistant within the first year. So we wanted to look at what's the effect of our treatment protocol on tumors that are resistant. And so you can see that those 2 growth curves that are growing faster, that's the TMZ or the temozolomide, the chemotherapy-treated animals, and the control animals. These animals are getting chemotherapy. That tumor does not care. It's growing just like a control. But the Cancerna protocol is effective, and when we add the TMZ and the Cancerna together, we actually get a further reduction in tumor progression. In other words, we ended up making those tumor cells sensitive to the chemotherapy that they were insensitive to. And so we mentioned a little bit about preventative stuff, and this was sort of an odd experiment that we kind of stumbled across. Basically, we had put animals on the Cancerna protocol for 2 months, and we were just leaving them on it. And we were doing it just taking blood work and looking for ketone and glucose levels, seeing how the animals did. Finished the experiment. We said, you know what? Why don't we inject a whole bunch of tumor cells into these animals, and let's just see what happens. And what happened, we used a model where we inject literally 1 million cells into the hip of an animal, and you can see that on the left-hand side in the control, 100% of the animals develop a tumor. But in the animals that were on this protocol for 2 months, there was a 60% reduction in the numbers of animals that develop tumors. And this was really surprising because we're taking 1 million cells, injecting them, this bolus, into the thigh of an animal. And when we do that in a control, it always develops a tumor. and only 40% of the animals developed tumor. And in the animals that did develop the tumor, the graph that's on the right-hand side, there was a slowing down of tumor growth by about, so their time to reach a certain size, it took them about 3 times as long to get to a certain size. And what about other tumors? So we've looked at colon tumors, and we've seen the same effect. Again, these are human tumors that are put into an immunocompromised mouse. We've looked at lung tumors. We see the same effect. We've looked at breast cancer tumors as well. And we've actually just finished a study where we looked at different subclasses of breast tumor, such as triple negative, HER2 positive, and a combination of those. And what we've seen is the same sort of effect. So even the different subclasses of the breast cancers respond to the treatment. And interestingly, some responded better than others. They didn't all actually respond the same. So the big question is, what are the mechanisms? And what we think is going on is something we call horizontal and vertical inhibition. And what this means is that we need to target tumors horizontally. In other words, we need to target multiple pathways. We can't just target one pathway. This has sort of been the modus operandi in a lot of cancer biology, picking one kinase inhibitor, one pathway, and targeting that. The other thing is we target them vertically. In other words, if this is a node within a pathway you're targeting, what tumor cells will do when you shut down that node is they'll actually go around that node and completely ignore it. So we need to target multiple nodes within the same pathway. And we need to target tumors metabolically. And so this is actually following the ecological principles that we were talking about. Using low doses and reducing the selection pressure of our compounds is management by multiple attack. Attacking sort of the escape mechanisms that tumors use, so this is being able to use multiple agents. So when you look at the things like the green tea catechine, you look at the curcumin, you look at the sulforaphane, these target collectively well over 50 different pathways that are active in tumor cells. So we're not just targeting one pathway, we're targeting a constellation of pathways. And lastly, we're using several individual stressors. And when we actually did this study and we came up with this combination, we found that each one of those things on its own, like the green tea catechine, the curcumin, or the sulforaphane, had very little effect. But it was the combination where we started to see these synergistic actions of it. And this is management by moderation. We got tons of mechanistic data and, things like, I won't go through all of these and talk about them, but basically pathways that are well-known drivers of tumor cell proliferation is we reduce the levels and the expression of many of those. And the last thing I want to just quickly talk about is something we ran across kind of by accident. This had to do with the side effects of chemotherapy. So some of the side effects you see in patients undergoing chemotherapy is anemia, low red blood cells, neutropenia, low white blood cells, chemo fog. This is where patients have difficulty remembering things like where did I put my keys, what was the last chapter that I just read in this book, and something called chemotherapy-induced peripheral neuropathy. And what we found was when we put animals, we called this chemo support, this experiment, when we put animals on this protocol, we found that the anemia was completely attenuated, the white blood cells was partially or significantly attenuated, and when we looked at sort of the pain index, so we would find these animals become very sensitive to pain. And this is very common for this chemotherapy-induced peripheral neuropathy, that we could significantly attenuate that, get it almost back to control levels. And when we looked at the neural stem cell population, animals that were treated with chemotherapy, you have neural stem cells in a part of your brain that are involved in learning and memory. And when those cells are not proliferating, you have problems with learning and memory. When you give chemotherapy, you reduce the proliferation of those cells, likely because you're actually killing that population. And we find that we could completely protect the neural stem cells in the brain that would be killed by chemotherapy by giving them this chemo support protocol. And we believe some of the mechanisms are actually related to cytokines. And so tumors themselves release cytokines, and when you give chemotherapy, you get upregulations of cytokines. And these are cytokines or inflammatory molecules that are having negative effects. And so we've looked at a number of different cytokines and seen that this is data just using the EDP alone, or the epidipherphane. We've seen the same when we did the EDP together with the modified ketogenic diet. But we get a reduction in these inflammatory cytokines. And so complex systems is, so things like an ecosystem is full, literally, of hundreds or thousands of interacting elements. And when you go and disturb one thing there, you get some kind of reaction to it. So aging of the brain, Alzheimer's, mild cognitive impairment, it's not just due to beta amyloid, it's not just due to one inflammatory molecule, it's due to a constellation of things. And aging is another example. It's not just due to one gene. There's a constellation of things that are going on. And so ultimately, we have to integrate multiple causative influencing factors and into our treatments, and also be aware of the negative effects that these treatments are creating as well. Because when they cause an imbalance in the system, there will be mechanisms that feed back into that to try to rebalance that. And that may not always be positive for the course of disease. And so virtually all biological processes in disease are caused and influenced by multiple drivers. And so the statement that we like to say in the lab is that multifactorial diseases, which is virtually every disease, require multifactorial drugs that simultaneously target multiple mechanisms. And so we call this combinatorial targeting. And ultimately, this is sort of the gist of what we're doing. This is the gist of the eco-oncology. It's taking these principles from the ecology world and applying them to the oncology world. But I don't think it stops there. It's not just going to be cancer, but it's going to be cognitive decline. It's going to be aging in general. It's going to be Alzheimer's disease, Parkinson's disease. These are all multifactorial diseases, and we need to target them at multiple levels. Thank you.